Hello and welcome to the video lecture series on contact mechanics in the course M7033T Scientific Computing with Applications in Tribology. My name is Andreas Arkes and I work at the Division of Machine Elements here at Luleå University of Technology. This is the second part of the third video lecture on contact mechanics algorithms, where we'll find out how to pose the contact mechanics problem as a linear complementarity problem. So for this video lecture, I recommend you, first of all, to look into the course compendium, which pretty much summarizes everything. But then also there is some specific papers that I think may be worth looking into. And one of those is the one by Tian and Bouchan, and the other one is the one by Stanley and Kato, which I have listed here. In this video, we start from the complementarity problem formulation, and we pose the contact mechanics problem on the form of an LCP, which we learned how to solve in the previous video. In the end, we will discuss the relation between the applied load and the interference or rigid body movement. Up to now, we have learned that we can apply Lemke's algorithm to solve a linear complementarity problem. So we could potentially apply Lemke algorithm to solve the contact mechanics problem if we can just find a good way of formulating the contact mechanics problem as a linear complementarity problem. Now, we know that the contact mechanics problem is a complementarity problem. And we have seen different examples of this. It does not have to be a perfectly smooth Hertzian type of contact. It can be a rough surface contacting a flat surface. It could be two rough surfaces contacting each other. It all ends up with this contact mechanics complementarity problem formulation, which we now have grown tired of seeing. We have also seen the formulation of the discretized formulation of the non-dimensional contact mechanics problem in terms of a complementarity problem. It looks like this for a 2D contact, which renders a 1D problem. And we have the linear elastic deflection. And because we have the linear elastic deflection, we will also see that we have a linear complementarity problem in this case. But it only applies to the case when we have a linear elastic deflection. And we have seen we can express U prime, the auxiliary deformation expression, with a kernel matrix times the discretization of the pressure. And it depends on how we discretize the pressure, what coefficient we find in the kernel K. Now the linear relationship between P and U prime via the kernel matrix K makes it possible to state the contact mechanics complementarity problem as a linear complementarity problem in this way. We learned previously that Lemke algorithm could be applied to solve the linear complementarity problem, and we also learned exactly when the solution will be obtained or how the solution will be obtained. And therefore I hope that we all now can easily conclude what the result would be in this case. Here we have an initial gap G, which is positive everywhere, since we have a positive interference. And just to remind you, we know that the solution to the linear complementarity problem would be given directly if all the components of B are positive, because then the solution would be obtained by specifying eta equals 0 and just read nu from the tableau as B. In this terminology with H and P as complementary variables, B would be G plus the dimensionless auxiliary representation of the interference, and it would be positive, it's clear, and then the solution would just be that the deformed gap would not be deformed, it would be G plus this auxiliary interference in non-dimensional form, and P equals 0 since there is no contact. Here we have a case where the interference is actually negative, so delta star bar is a negative number, meaning that in combination with this parabolically shaped undeformed gap G, we have a starting point for a non-trivial solution P and H of the complementarity problem. But how can we specify the load? This is a question to you. We understand that there must be a relationship between the applied load and the interference, and normally the interference is not known, but the applied load is. And we have seen that we can formulate the expression for the dimensionless applied load either by this summation type of formulation or in vector matrix form like this. Moreover, we know that the deformed gap is given by this linear relationship to the pressure P. And where there is contact, we know that the deformed gap is 0. And this means, of course, that if the left-hand side of the equation is 0, then the right-hand side of the equation is 0. And we can solve P from this equation by matrix inversion, or solve it by Gaussian elimination. Which means that we can plug it into the expression for the applied load, and we can clearly see that the applied load is linearly related to the interference. And this is illustrated in the figure down here. Let us now try to construct the kernel matrix K in the expression for the auxiliary deformation U prime equal KP. So if doing this in MATLAB, we should start with MATLAB's first commandment, clear all. Next should be followed by an input section, which in this case is very simple. It's just the number of nodes and the computational domain. We note here that I've used 2 to the power 8 plus 1 to define the number of nodes, and by doing so I can modulate this exponent 6, 7, 8 or so, and that by that doubling or halving the step size and verifying, validating the method that I'm trying to construct. So a very useful way of defining the number of nodes. Next would be the pre-processing stage, and in this case it's also very simple. It's just the interval length, the mesh step size, and the discrete domain. So nothing strange with this. When having the domain, discrete domain defined, we can define a pressure profile, and in this case we're going to define Hertzian pressure profile to compute the auxiliary deformation U prime. And then this may be done in MATLAB like this. You find the indices where x lies between -1 and 1. You predefine your pressure vector by a vector full of zeros with length n, and then at those indices where x lies between -1 and 1, you just add a semicircle. In this way we have constructed a Hertzian pressure profile. Okay, you can see here beneath I have commented away another pressure profile, which would be equally interesting to study actually. And it's a sinusoidal one, or co-sinusoidal one with the addition of some disturbance or extra roughness, if you like. You can try and explore that yourself and see what happens to the deformation equation, if you like.